Assalamualaikum and very good day. Welcome back to mechanism design or kinematic design. So today we are going, or in this video, we are going to go through the topic of linkage velocity analysis. So I'm gonna share my screen. So in this, we are going to use several methods, namely the vector method as well as the graphical method, and also vector method as the analytical method. So linear velocity is basically we need to talk about speed and also velocity. Speed is when we measure how fast an object moves. It is a scalar unit, time unit, distance over time unit. Whereas velocity is not just the magnitude of the velocity that is what matters, but also the direction. So velocity has speed as well as the direction of the speed. So VB is the velocity of point B, whereas VC is velocity for point C. If you look at this diagram in this slide, we have this thing. So depending on the direction of rotation of this this body, so this is basically a ternary body or ternary link, where we have three important points, A, B, and as well as C. So it is one single body, not two, because we have this thing, meaning that this angle between AB and AC are fixed. So they are going to be moving or turning or rotating as a single body. So for the linear velocity, it is pointing this way perpendicular to this the direction or the radius between A and B, whereas C is pointing that way because it is perpendicular to this link, AC. Common units usually for the linear part, linear velocity is meter per second, feet per minute, FPM, mile per hour, kilometer per hour, and so on and so forth. Okay, so oftentimes if we know the direction and also the radius, we can get what is the direction of the linear velocity. Whereas for the angular velocity, it is the how fast the arm rotates or the body rotates about a certain point or center of rotation. And then the unit that is commonly, units that are commonly used are RPM, radius per second, as well as degree per second. In some computer programs or CAD, they allow you to set the speed, the angular speed as degree per second. Okay, so but in a lot of readings, such as the meter panels on our vehicle, car or motorcycle, the engine speed is given by RPM. Whereas in a lot of our calculation, we have to use radian per second. That's why you need to always know how to convert between RPM and RPS. And there is also always, when we talk about rotation, we always need to know that there are two directions, either clockwise or counterclockwise, or sometimes they call it anti-clockwise. But the short form for that is CW for clockwise and CCW for counterclockwise. And the main relationship between the angular speed or angular velocity and linear speed or linear velocity is V equals to R omega. Omega is the angular speed, R is the radius, and V is the linear speed, linear velocity. And in this, the unit preferred for omega will be radian per second. So because you need to know, in this situation, the V is probably a meter per second, in meter per second. So in that case, R is in meter, and omega must be in radian per second. Radian per second. A radian is kind of like unitless. So this is one example, or example one, velocity of a point C. We have to refer to a figure, and that linear velocity is 10 meters per second. So we have to determine the velocity of point B. I suppose we have a ternary link. If the link, the overall link is rotating clockwise about pivot A. Let's take a look at that figure. Here it is. So the ternary link is rotating clockwise about point A. And we have VC is already given, 10 meters per second. And this is longer with RAC equals 38 cm. 20 centimeter, whereas RAB is 25 centimeters, and the direction will be different. Linear direction will be different, but the angular speed are the same, which is omega. And we can find that omega from the VC that we already know, and we can divide VC over RC or RAC, and we get 26.32. And this omega equals to 26.32 is the same omega that is going to be used or felt by point B. So we can find what VB is by RB times omega, the same omega. And that should give us 6.58 meters per second. So you see, as the RC or the radius is longer, the speed is going to be higher, whereas when it's shorter, the speed will be lower. And that understanding should be used when we discuss linkage, linkage like this, like the 4-bar mechanism. So for 4-bar mechanism, we do not have just one link rotating, but the links are joined with other links, and in this case we have two fixed pivot at A and D, and two moving pivots at B and C. So the linear speed VB we can assume as to be the given, that is part of the input VB. Maybe if not, maybe something that you can find out. Maybe the given input is the angular speed at AB, and then we can calculate what BB is. So this is solvable. So you can consider this as the input. You should know what VB is. And then you see at point C, there are two bodies that are sharing that joint C. So we have this link BC and also link DC joined over there. So that's why we have two lines. One is perpendicular to this link, whereas the other one, BCD, is perpendicular to link DC. VCD, VC/D, meaning the velocity of point C with respect to D. So that is, and point D is in the point C is in the what you call, point C is in the ground. Oh, sorry, point D is in the ground, so that is fixed. So sometimes we call this just C. Whereas this line, this other line is VC/B, and C and B are both floating points or floating pivots. So this one will maintain. So meaning this is VC at point C with respect to B. So in that case, we are assuming that this link is going to rotate about point B. So usually the ground, if we do the numbering, so ground is number 1, so this is number 2, this is number 3, and this is number 4. All right, so we can use that. Okay, we can also have we change color, ink color. Okay, we can also have perpendicular over here. We do not know whether it's going that way or this way. So it's supposed to be perpendicular. If this is the case, then this one will be VB/C. So C is the point of rotation, and the velocity is acting at point B. Okay, so whatever it is, usually the magnitude for either case, they want to go with this one or that one, should be the same. The magnitude should be the same, but maybe the direction will be opposite. Okay, like I said, this VB or VB/A. Okay, so can say this is also similar to VB/A, but since A is in the A is a fixed pivot on the ground or on the frame, so usually we just drop it because it's not floating. Point B is floating, point A is fixed to the ground, so we just say VB. So since this vector is known, you know the magnitude, we can calculate that. So we are supposed to be able to calculate that, and also the direction is already established. So we just start with that. We set the tail as the origin OV, so the origin OV, and we start from there. And then what the other two, we know VCB, we know the line of action for VCB. So since VCB needs to be in touch with point B, so we draw that at the tip of vector B, vector VB. Whereas VCD is related to point D, and that is related to the ground. So we must pass through the origin. So origin in this vector polygon is the 0, 0, is the ground. So this is the ground. So this is ground. How do I write that? Maybe I use my magic pen. So over here, so this is ground. This one. So that is ground. Does it look like ground? It better be. Okay, so once you draw these two lines that needs to be accurate, you will get the point of intersection. So once you get that, your problem is already solved. Okay, you just VCD or VC needs to be from origin outward. Cannot be from here to there. It must always start from the origin outside. And this one, you have to ask yourself. Okay, so this will be point C. So if you want your velocity here to be VCB, so it needs to be pointing from B to C. So if it is VBC, meaning it is from C to B. Okay, so you got to understand that. So you can also have that direction. Okay, it's not the, but this one will be VB slash C. Okay, same magnitude, same length. So you got to be able to measure this length, and the direction is just opposite. Must be following this line of action. Okay, that's what we just finished is the analysis of velocity for 4-bar mechanism. Whereas for slider crank, which is also another important kind of mechanism, basic mechanism, so it is a little bit different. Let's see how it is different. So in this example, you have a 10 cm crank. So this is crank, where usually a crank is something that the input that can rotate full 360 degrees. And it is rotating at 100 RPM counterclockwise, CCW. The connecting rod, which one is connecting rod? Link number 3. And this is 50 cm. And this is the offset. This will be R1. That is 7.5 cm. Crank angle at this moment, meaning the input number 2, is at 30 degrees. So we need to find what is the speed or velocity of this piston in this condition. So since so you have to draw the link exactly. In this case, I use AutoCAD. So you want to be as accurate as possible. So I draw this 10 cm crank at 30 degrees. So if you measure, this should be 30 degrees, pointing that way. And then you have this 40. Actually, it should be 50. So I don't know which. So in this case, it's supposed to be 50. So let me change that to 40. I think that is doable. Save this bad boy. And then so from here we should get be able to get 105. 105. 105. So I believe VB supposed to be R2 times omega, and that should be 10 times omega is what? 100 RPM. So that is 100 RPM. So you have to change it by using this what call this conversion factor pi over 30. Why is that? Why is that so? So because 2 pi radian revolution. 2 pi is 1 revolution. 2 pi radian is 1 revolution. And then you have a second because you're converting from RPM revolution per minute. So you want to convert it to radian per second. So revolution is cancelled here. Minute, so you have 1 minute. 1 minute is 60 seconds. 1 minute 60 seconds. Then 2 divided by 60. So that gives you this conversion factor over 30. So this will be mean revolution second, something like that. So that's why we use this conversion factor. Okay, and that's the origin of this one. So that explains, and this one should give you 1.05. And in this case, I guess this is in centimeters, so I have to change it so that won't be too long. Otherwise, this vector will be too long out of the space here. So I just change it from, instead of having centimeter per second, I have it in meter per second. All right, and then so you by drawing this, you already solve. So this will be R1. So this will be R2. So suppose this is R2 is 10 cm. So this is R1, 7.5, and all the way here. This should be your R3, and this is R4. Okay, so that something that we should be able to solve for. So in this actually, this is something that we want to solve for. Another one that we want to solve for is this angle. What is this angle? So this should be theta 3. So I think I did not measure here, but that is something that we should be able to do. Okay, and in this case, since this 1.05 meter per second is already known, so over here will be the origin, and we can this will be the direction of the slider of the piston, and this is the direction that is perpendicular to link number 3, which is the connecting rod. And we can measure what's the length between this point to the intersection, and this meaning our omega 3 VC/B is 0.96 meter per second, whereas for the slider it is 0.82 meter per second for the slider. And slider needs to be pointing this way, away from the origin, and this meaning this is point C. So if I can label, so this will be point B in velocity, and this is point C. So this is origin velocity. B. Okay, so that is the case. So, yep. So if I use, this is the angle 108, negative 108. Why? Because this angle should be pointing in the clockwise direction, hence it is negative, as opposed to something that is counterclockwise, which is positive. So we always say this one is positive angle, whereas this one is a negative angle. Okay, and we get this 0.96 and heading in this direction, and through calculation, if you do your drawing using manual, so you need to have your jangka sudut, what you call jangka sudut, compass, protractor, and then you should be able to get the accurate reading. And you see, if you take the the magnitude for this one, for this vector, using root sum square, you should get VC equals to negative 0.82. So negative 0.82 meter per second is to the left. To the left. Eraser. Let me use my pen. This is the, so it's pointing to the left. To the left. All right. Vector analytical method. Vector analytical method is something that we can also use. So just like in the lecture on position analysis, because when we do the velocity analysis, we must also solve the position analysis first. You must, if in the case of 4-bar mechanism, usually theta 2 will be the input. So we have to solve for theta 3 and theta 4. Okay. For slider crank, if theta 2 is the input, you have to solve for R4 and also theta 3. So always identify or realize that this loop where you have 4 sides here, denoted by R1, R2, R3, and R4, can be broken into 2 triangles. They look like rhombus or something like that. And we can have 2 triangles actually, where the first part is already known. So when this part on the top, top right, you have R1, usually that is known, and R2 is the given, or you have to decide that. And from there, you can get R5 or whatever you want to call it, maybe RH, something like that. So if I label the imaginary vector in the middle as R5, so when I convert this from vector to scalar, you get this triangle, and you can work with the scalar scalar part of the vector, where we have on the lower part, on the lower left part, you have R5, R3, and R4. In this situation, this vector R4 and R3 are not completely known yet, because this angle, the direction, their angles are not set yet. It's not determined yet. So that's why you get out from vector into scalar part, and you try to use this the cosine or sine laws in order to solve for these angles. Okay. So angle alpha here, you can solve for that. Once you know all these scalar lengths, R5, R4, and R3, you can solve for alpha. And once you do that, R5 is also known. Okay, maybe it's not labeled that yet. So maybe should this theta 5 is already known. So theta 5 is already known, or you can solve for that. Okay, so here theta 5 can be completely determined. Here we can find what is the direction and also the magnitude of R5. Okay, and then the next level, number 3, you bring it into this second loop. This is the second loop. This is first loop. First loop. This is second loop. So, and also this is the second loop. Second loop. So once you have determined the position, you can differentiate stuff, and you can solve for whatever that you want to solve for. Okay, let's take a look at this other example. So you have this 4-bar mechanism, and in this case, except for this case, we have a floating point X on top of the link number 3. So actually your link number 3 is a big one. It's a ternary link instead of a binary link. So link number 3 has points B, C as well as X. Okay, if I can use my pen here. So here we have link number 1, always at the ground. So this is link number 2. This whole thing is link number 3. And lastly, the last one is link number 4. All right. So you, based on what you already know, the crank is 15 mm. I guess it's 15 cm. Might have. I think it's 15 cm instead of mm. Let me check. 15.7 meter per second. Let me check that calculation, see what unit it should be. So 15 times, what was the 1000 RPM? So 1000 RPM and times pi divided by 30. And then I want to divide by 100. So it should be cm instead of mm. So let me fix that. Sorry for this mistake. So this one should be cm. Okay, and then so if you do the calculation right, so what should be, so, and this one I was going counterclockwise. So meaning this one is going in that direction. So meaning this velocity over here needs to go in that direction. So this will be your VB. This is VB. V all right, VB. And we can calculate that to get 15.7. And how do we do that? How do we calculate that? So B equals to 15 divided by 100. That is our 15 cm over 100 to convert it into meter. Okay, to meter. That is our R, and then our omega is 1000 RPM. And we have to convert that by the conversion factor. And that should give you 15.71 meter per second. So that will be this direction. Needs to be perpendicular. This is 90 degrees over there. Okay. And then I usually need to just draw so that we are aware of the perpendiculars lines perpendicular to each of the sides. So for this ternary link, even though it's supposed to be one ternary link number 3, but it has 3 sides, so each side needs to have that perpendicular lines. So the side that really connects point B and C will be this one. And this one will be perpendicular for this one. This is for line C, VC. So if so this is point C, this is point B, this is A, D, and this is for VC, this is for VC/B, okay, and so on and so forth. Okay, so this is for VX/C, and lastly, this is for VX/B. Okay. All right. Are we clear on that? So this is using graphical method. So we always start with the information that we already know, which is VB. VB, that is 15.7 meter per second, and we know that direction. Draw that, and the tail is where the origin will be. Then we take the line for VC and also VC/B. VC and VC/B, and you'll get this intersection, and just draw them, label them accordingly. So this will be VC, VB, and this will be VC/B. Okay, but we need to find Vx. So we need to extend. So the line that Vx/C must pass point C, whereas Vx/B must pass through this one, through line point B. So these are the remaining two lines that we need to include in our vector velocity polygon. Okay, so once you do that, you see another intersection, and that will be point X. Okay, so if you want Vx from the ground, Vx from the frame, you take all the way from OV to point X. So this black arrow will be the one that is your concern, and that comes to about 18.03 meter per second. 18. Okay, so you can also do it analytically using vector, and you should get the same answer. Okay, so I guess we will continue on that one next time. So for the rest of this, so I'm going to stop here for this edition of the lecture, and I hope to see you guys in the next video, which I will record as soon as possible. Thank you. Assalamualaikum, and have a good one. Bye-bye.